So hello everybody, welcome to lecture 1 of chapter 3, that is current electricity. So when we are dealing with this chapter, let us first of all begin with the basics about current. So what do we mean to say when we say current? So before coming to the mathematical definition of current, I would like to throw some examples. So in the previous two chapters we have read about the charges which were at rest, and we studied about them considering the fact that they are at rest and named it as electrostatics. Now there is always some phenomena that is occurring around us in which the charge is flowing from one point to another, and one such example is lightning, which is a natural phenomena. In case of lightning, the flow of charges is taking place which is not steady. So over here I am using the word steady, but in the cases where we study generally about current, that is the current which is flowing through a wire, is an example in which we say that there is a steady flow of electric current taking place. So basically we can say that in case of lightning or a natural process, the flow of current is not steady and we call it as unsteady flow of current. And in the other case which I said, a wire, an electric current carrying wire, is one in which the flow of current is steady. So this rate of flow of charge between 2 points, which is having a certain value of potential difference, is regarded as current. So when we define current, we define it as the current across the area is regarded as the rate of flow of current, and hence mathematically we write it in this way, that current as a function of time is written as limit delta t approaches 0 del q by del t, and we define it as the current is defined as rate of flow of charge, and we write I is equal to dq by dt. So we write value of I current as dq by dt, which is also regarded as the rate of flow of charge. Now over here we also write it as I is equal to charge flown by time taken, when we are writing the average value of current over a certain instant of time, over a certain span of time. And this is one definition where we find the current as rate of flow of charge, that is dq by dt. Now if we come to the unit of current, we say that the SI unit of current is ampere. When we write ampere, A is small. So SI unit of current is ampere, and the smaller units which we use often is milliampere, which is 10 to the power minus 3 ampere, microampere, which is 10 to the power minus 6 ampere, and so on. So let us understand the current flow using one more detailed diagram. So we are considering something like this, that there is a sphere A which is positively charged, and we consider another sphere B which is slightly less positively charged, but they are identical in terms of geometry, that is they have the same radius and made from the same material. Now if I join A and B using a conducting wire, so over here I say that the number of electrons in B is greater than the number of electrons in A, or I can say that the electron will flow from B to A. Electron flow will take place from B to A. The direction of conventional current is taken opposite to the direction of electron flow, and we say that the current is flowing from A to B in this direction. Now if I define it in terms of the terms which we have learnt before, so I would say something like this, that the sphere A is at higher potential, sphere A is at higher potential, while sphere B is at lower potential. While sphere B is at lower potential and the current is flowing from high potential to low potential, and the current is flowing from high potential to low potential. So this is how we say that the current flow is taking place between the two conductors or between the 2 points, that the current is flowing from a high potential to low potential. Now when I say that current flow is taking place, so now to understand more, we wish to understand about the nature of this current carrying wire. We wish to understand about this current carrying wire through which the current flow or the electron flow is taking place. So in order to understand exactly how the electron flow is taking place, with what velocity and with what constraints these things are taking place, so let us discuss in detail about the current flow through this current carrying wire. And the model which we are discussing is regarded as Paul-Drude model. So over here we are considering something like this, that the current carrying wire, which I am drawing in a bigger way, consists of a large number of electrons which are free electrons. Now anything which is a solid is regarded as a conductor if it contains a large number of free electrons. Now free electrons are those electrons which are moving through the metal lattice. They are not coming out from the metal lattice, but they are detached from their parent atom so that they can move throughout the metal lattice. And over here there are some fixed positive charges also, which are developed because the atoms are devoid of electrons, and these fixed positive charges are called as kernels, Kernels. Now we are saying, as there is a potential difference, the electron is drifting from one end to the another. So I am saying that the electron is moving from one end to another like this. So the electron is moving from that end, that is my right end, to the left end like this, and we consider that this end is of end A and this one is of end B. So A is at higher potential in comparison to B, so the direction of current flow is opposite to the direction of electron flow, so the current flow is from A to B. So initially when no potential difference was applied, so all the electrons inside this system of wire were in random motion. So when I say they are in random motion, so I mean to say that some electron are moving towards this direction, some are moving towards this direction, some electrons are moving towards left, some are moving towards right, some may be moving in the upward direction, such that their net velocity, so their net initial velocity can be considered as zero. Now the moment the potential difference or an electric field is generated because of the potential difference existing between the two ends of the conducting wire, the electron flow becomes civilized and they start drifting from one end to the another with a certain value of speed which is regarded as drift velocity. Now if we start considering this, so we are considering that if suppose an E electric field is generated across the ends of conductor, an electric field E is developed across the ends of conductor, then the electron will experience a force due to this electric field which can be written as EE, where E is electronic charge. And if we write F as MA, so from here we obtain a value for the acceleration, and this acceleration value can be written as EE by M. Now if we consider the value of velocity, so using the classical approach, V is equal to U plus AT, where the time we are using is tau, that is relaxation time. We will discuss about it soon. So we obtain a value of drift velocity as EE by m tau. So this is the equation for drift velocity which we have for the electron as they are moving from one point to the another through this conductor. Now if I consider that the number of electrons, or basically we say that the charge density is n. So now we are considering, we are moving to the next page. So we are considering if n is carrier charge density, if n is carrier charge density and A is cross sectional area of the wire, cross sectional area of the wire, and we are considering the length of the wire as L, about which we are studying this entire effect. So I can say that the number of charge carriers, or the number of electrons, the number of charge carriers can be written as NAL, and hence the charge flown, the total charge flown in this region can be written as NEAL. So this is the charge that is constituting in this area of cross sectional area A and length L. And if I write the equation of current flow for this particular region, so I can say that therefore the current flow can be written as charge flown by time taken. So I can write it as NEL by time t, and we write this L by t as drift velocity, NEAVD. So if the electron drifts a distance L in a long time t, we define the drift speed as Vd is equal to L by t. I am repeating one more time. If the electron drifts a distance L in a long time t, we define drift speed as L by t. So we have some equation something like this for the electron flow, or the for the current flow. I is equal to NEAVD. So this is the expression which we have obtained. I is equal to NEAVD. Now from the previous page, we have obtained an equation for drift velocity as EE by m tau. So if we put it over here, so from here we can write from the equation of drift velocity Vd EE by m tau. So we can define current mathematically as NEA EE by m tau, and this equation is going to modify as I is equal to NE square tau by m. into area A and electric field E. So this is the expression which we obtain for current. Now over here we are defining one more interesting term which is regarded as current density. So let us discuss about current density over here. So when I say current density, so current density is a vector quantity. Current density is a vector quantity and it is defined as the current through unit area normal to the current. So current density is defined as the current through unit area normal to the current flow, and that is we define it mathematically as J vector is equal to I by A. So current density is defined as the current through unit area normally to the current. So we are considering this as the definition of current density, and from this expression I can write current density, that is J vector. So we can write J vector which is equal to I by A as NE square tau by M into electric field E. Now this expression in bracket is regarded as conductivity of the wire. Ne square tau by M is referred to as conductivity of the wire. And we write this expression as J vector is equal to sigma E, and this is regarded as physicist form of Ohm's law. So this expression J vector is equal to sigma E is regarded as the physicist form of Ohm's law, where sigma is equal to Ne square tau by M. Now we will be modifying this expression which we have obtained over here. So we can modify this equation in this way. So from the previous page we have obtained J is equal to sigma E, which is physicist form of Ohm's law, where J is equal to current density, that is I by A, and sigma is equal to Ne square tau by M into electric field E. So if we wish to understand this equation in terms of potential difference, so I can say that for a current carrying wire, in which the electron is drifting from one end to the another, the electron is drifting from one end to the another, I can say that if the length of this wire is equal to L, so we can say that the potential difference is equal to E into D, and hence E is equal to potential difference upon length, where we can say D or L is the same thing. We are using L over here, that is length of the wire. So it can be written as potential difference per unit length, and hence this expression can be written as I by A equals Ne square tau by M into potential difference per unit length, that is V by L. And from this expression I can say that potential difference is equal to M upon Ne square tau into L by A multiply by current. So now this expression which we used over here as conductivity Ne square tau by M is in the reciprocal form in this equation, and we call it as resistivity. So resistivity rho is equal to M upon Ne square tau. So the reciprocal of conductivity is regarded as resistivity. Reciprocal of conductivity is regarded as resistivity, and we write this expression as rho L upon A times I. Now when the physical conditions and temperature remains constant, we call this term rho L upon A as the resistance of the wire. So resistance offered by the material, and it will remain constant when the physical conditions and the temperature is unaltered, and we obtain the expression for Ohm's law, which we generally use, V equals IR. So using Paul Drude model, we have assembled or basically derived Ohm's law. Over here, one thing must be kept in mind, that any law of physics is not derivable. Basically, this model of Paul Drude came much later in comparison to the law which was given by George Simon Ohm. So the idea of Ohm's law was established much before the Paul Drude model. So the Paul Drude model was just given to explain the nature of the current flow through the ohmic conductors, and a few aspect of it is also applicable for non-ohmic conductor, which we will be discussing very soon. So if we come to the definition of Ohm's law, so we are discussing about Ohm's law or the work of George Simon Ohm. Now before coming to the conclusion that potential difference or the current flow is directly proportional to the potential difference across the terminals, Ohm established a circuit like this. So there was a resistance R attached with a variable resistor, which we call as rheostat. The current flowing through this circuit was measured using an ammeter, and there is a DC source attached with a key, and the end is connected to the rheostat with the help of a jockey J. So now as the current is established in the circuit, the potential difference across this resistor V and the current in the circuit is measured by an ammeter A for the different values of resistance, which is changed in this circuit by changing the position of this jockey J, and a table like this was obtained where the value of current and potential difference were noted. So different values of current and potential difference were noted like this, and then Ohm plotted them in a graphical representation drawing V and I graph. So V and I graph was obtained, and the graph was obtained to follow a straight line something like this, and from here the idea of Ohm's law originated, where he stated that the current flowing in the circuit, the current flowing in the circuit is directly proportional to potential difference across its end, is directly proportional to the potential difference across its ends, provided the physical conditions and temperature remains constant. Provided the physical conditions and temperature remains constant. And post this law, after some years, the Paul Drude model was given to explain the working of this particular Ohm's law. So it must be very well kept in mind that the laws cannot be, they are not derivable, they are based on observational facts. So as we move ahead, So we will be understanding this particular statement as to why there are conditions. So over here the condition is the physical conditions and the temperature must remain constant. So we want to understand over here as to what variation will come in with the change in temperature. How is it going to affect the resistivity or the resistance offered by the material, and will it be same for all the types of material? So if we understand this, we come to the first aspect or a few more definitions which are left out. So the first thing that we will be discussing over here is the limitation of Ohm's law. So let us discuss the limitation of Ohm's law. So the first limitation of the Ohm's law is that it is applicable only for ohmic conductors. It is applicable only for ohmic conductors. And on the other hand, non-ohmic conductors are those conductors which do not obey Ohm's law. So for example, we say that the ohmic conductors are those conductors which follows V proportional to I. So the current flowing through these conductors is directly proportional to the potential difference across its end. But in cases of gallium arsenide or for silicon or for germanium or any other semiconductor, the variation of V versus I or I versus V is not a straight line graph. So it follows a non-linear graph that is something like this. So if we draw a graph for a typical semiconductor, so in the y-axis we are measuring current in milliampere, and in the negative y-axis we are measuring it in microampere because the value of current is less in the reverse bias voltage. We will be studying them in detail in the chapter of semiconductor, and the graph like this is obtained for semiconductors. For gallium arsenide the graph is more interesting. So for gallium arsenide the graphical representation is something like this. It is something like this. So over here we are measuring current in milliampere and the voltage is in this side. So and the graph is divided into sections which we call it as this first part is the linear region, the other one is the non-linear region. So this one is non-linear region, and this one is a region where the resistance is negative, so we call it as negative resistance region. So this one is a negative resistance region. So the relation between V and I is not unique, and there is more than one value for potential difference for the same value of current in the material like gallium arsenide. So these are the limitations associated with Ohm's law. So now we will be discussing about the reason behind the resistance. When I say I will be discussing about reason behind the resistance, so I basically mean to say that there are many a times that the student comes up with this very interesting question. According to them, it is very interesting. They think why resistance is regarded as obstruction in the path of flow of current. Basically the theme of this question which they ask is why the electron flow doesn't get stopped, why the electron doesn't get consumed, or rather why the current do not deplete while going from one end of the wire to the another, why there is only obstruction in the path of flow of current. So when we say resistance, we mean to say The obstruction in the path of flow of current is regarded as resistance. The obstruction in the path of flow of current is regarded as resistance. It is measured in ohm, and when we talk about resistivity, so I say R is equal to rho L upon A, and from here if we find out resistivity, then it is Ra by L. So I write the SI unit for resistivity. So SI unit for resistivity of the material is written as ohm meter. Now since conductivity is reciprocal of resistivity, we write SI unit for conductivity as ohm minus 1 meter minus 1, which is also written as Siemens per meter. So we are coming back to the problem. What is the reason behind resistance and why the wire is not consuming the electron which is flowing from one end to the another? So let us understand it this way. So if we consider that this is the current carrying wire and there are a large number of free electrons. So when I say free electrons, what do we mean to say by free electrons or free charge carriers? We mean to say that these are those electrons which are helping us in conduction, and they are regarded as a part of conduction band. So basically we have divided the electron into two parts, conduction band and valence band, and there is a slight energy gap between the valence band and the conduction band. If we talk in terms of conductor, the valence band and conduction band are basically merged into each other or fused into each other. So that is, there is no gap between the valence band and the conduction band in case of a conductor. Whereas in case of a semiconductor, there is a slight energy gap between the valence band and the conduction band. So we can consider it in the diagram like this, that for a insulator, if I draw, so this is the conduction band and this is the valence band, and there is a large energy gap in between them. I call this energy as Eg. So this one is an example of an insulator. When we talk about a semiconductor, so the gap between the conduction band and the valence band is reduced. So this one is conduction band and this one is valence band. So in case of a semiconductor, so this energy gap Eg is reduced, and in the case of a conductor, the conduction band and valence band are fused into each other. The conduction band and valence band are fused into each other. So this is regarded as a conductor. So these free electrons over here are in the conduction band. So, and there are also fixed positive charges which I already taught you. So as these electrons leave the atoms and they are going around the lattice of the metal, so it must be also kept in mind that these electrons are not coming out from the metal surface of the body. They are basically moving through the metal lattice from one point to the another, helping us in conduction. So that is why they are named as conduction band. So now as these electrons are drifting from one point to the another, we are considering something like this, that the electrons are moving from this end to the another end like this. So as they start moving, there is a attraction because of the fixed positive charges, and as a result of which they collide. So the average time between the collision is regarded as relaxation time tau. So this is the average time between the two successive collision which is taking place. So now as we increase the temperature, the average speed of the electrons which act as the carrier of current increases, resulting in more frequent collisions, and the average time of collision or the relaxation time decreases with rise in temperature. So I say that as temperature rises, the relaxation time decreases. So basically I mean to say that as the electrons are drifting from one end to the another end, there is a tendency that they can collide with the fixed positive charges, and the average time between the two successive collision is regarded as relaxation time. Now after collision, these electrons will come to rest and will again start drifting in the same direction. Now this one is an interesting part where people feel that how is this taking place, they find it difficult to visualize. So over here I am giving you an analogy as to how to understand this entire concept. So we consider it like this. So let us consider an inclined plane, and we are fixing some nails on this inclined plane. This one is a fixed inclined plane otherwise, and is perfectly smooth. That is, it do not offer any frictional force, and the electrons, or basically you can say that these table tennis ball are projected from the top of the incline, as a result of which these balls start moving down like this. Now in their path while moving down, there is a chance that they can collide with these fixed nails, and they will come to a momentarily halt. They will come to a momentarily halt, but because of the potential gradient, that is the gravitational force acting in the downward direction, they will continue to move in the downward direction post collision. They will start with zero velocity and again start drifting in the downward direction. So this is what the analogy is. So all the balls which are projected from the top of the plane is definitely going to reach the bottom of the plane. So we say that as the wire is kept and the electron is flowing or the current flow is taking place, the current is not getting consumed by the wire. It is only offering obstruction in the path of flow of current. So this can be understood well with this analogy. So we say that as the temperature increases, the relaxation time decreases. So this is the first parameter that we also came through, which will help us in the study of variation of resistivity with temperature. And also one more point can be noted from here, that over here in case of conductor, the value of free charge carrier, that is small n, is more or less fixed. It is because the conduction band and valence band is already fused with each other, and the electrons can easily move from valence band to conduction band. So as the temperature will rise, the value of number of free charge carriers increases, because due to the rise in temperature, more electrons will acquire the energy and will shift from the valence band to the conduction band. So for the semiconductor, as the temperature is increased, there is a considerable increase in the value of n. There is a considerable rise in the value of n. There is a, or you can say there is a significant rise in the value of n. So I am writing over here that as temperature increases, n increases, and as temperature increases, tau decreases. And for a semiconductor, there is a significant rise in the value of n, because there was an energy gap between the conduction band and valence band, and as this temperature rise is provided, the electrons will move from the valence band to the conduction band. So now if we come to the study of variation of resistivity with temperature, variation of resistivity with temperature. So I am writing the equation of sigma and resistivity which we have deduced earlier. That is, sigma is equal to Ne square tau by m, and hence resistivity, which is reciprocal of conductivity, is m upon Ne square tau. So over here I can say that since E and m are fixed parameter, so the parameter of sigma and rho is depending upon n and tau. So now as temperature increases, we have explained earlier that as temperature increases, so as there is a rise in temperature, we say that the relaxation time decreases and n increases. So over here, since the value of sigma is directly proportional to n tau, so now we are in a fix, because one parameter is increasing with the rise in temperature and the another parameter is decreasing with the rise in temperature. So I say that for metals or conductors, relaxation time decreases significantly, significantly, whereas the number of charge carriers increases less significantly, because already there are a large number of carriers which is present in the conduction band, and hence we say that the overall parameter n tau decreases with temperature, decreases with temperature. And hence I say that as n tau is decreasing with temperature, the value of sigma also decreases with temperature, or I can say that it's reciprocal, that is resistivity is increasing with temperature. So this is the first notable fact over here as to how the value of resistivity is affecting or getting varied for a conductor. So if I draw it graphically for the conductor, so I can say that overall that as the temperature increases, the resistivity increases with the rise in temperature for a conductor. So if we see the graphical variation, so the graphical variation for copper, if I draw the graphical variation of resistivity of copper with temperature, so I'm writing for copper. So the temperature variation with resistivity is obtained something like this. So it is obtained something like this. So this range of temperature is lesser. So over here we have 50, over here we am writing 100, and over here we are writing 150, and this temperature is measured in Kelvin. And over here the resistivity is in 10 to the power of minus 8 ohm meter. 10 to the power of minus 8 ohm meter. I can say that by the time it reaches room temperature, that is somewhat around 300 Kelvin, the graph will become almost linear. The graph will become almost linear. And similarly, I can draw a graph for the variation of resistivity with temperature for a nichrome wire. So I'm writing for nichrome wire, and this time we are drawing near room temperature. So near room temperature, the graph is linear. So this graph is linear near room temperature, and we use a relation to explain this. So the relation which we are using as the variation of resistivity with temperature is, so resistivity at a temperature T, or the T change in temperature, is equal to rho naught 1 plus alpha T minus T naught. So this is the variation of resistivity with temperature equation, which we can write for a particular metal. So over here we say that rho naught is the resistivity at a reference temperature T naught. So rho naught is the resistivity at any reference temperature T naught, and as the temperature is raised above this reference temperature, that is at a temperature T, the value will become rho suffix T, rho T, and it is proportional to the dimension alpha. So the change in resistivity is proportional to alpha. We can also regard it as the coefficient of resistivity. It is also regarded as coefficient of resistivity. Coefficient of resistivity. So if we again consider this equation which we had, that is sigma is equal to ne square tau by m, or rho which is equal to m upon ne square tau. So again, if I say that as temperature increases, the value of tau decreases and the value of n increases. So this time we are talking about for semiconductors. For semiconductors, we say that n increases considerably. N increases considerably, and as a result of which a large number of carriers shifts from the valence band to the conduction band, and hence I say that the n tau value increases, and as the n tau value increases, the conductivity increases, and hence resistivity decreases with the rise in temperature. So as temperature increases, as temperature increases, resistivity decreases with it for semiconductor. For semiconductor, and if we consider it graphically, we can draw a graph like this for a typical semiconductor. So we say that the variation of resistivity with temperature is taking place somewhat like this. Resistivity is decreasing with the rise in temperature. So this is how we study the variation of resistivity with temperature and the resistance with temperature for different varieties of materials. So in this part we have dealt with the introductory part, that what is the definition of current, and then we have dealt with the Paul-Drude model where we have tried to establish Ohm's law, and then we learnt about the variation of resistivity with temperature and how the resistivity is increasing or decreasing with the change in temperature.